much, Brian. So, hi everyone. I'm mindful of the fact that I'm the only person between us and getting ready for dinner, so we'll keep this talk very efficient. So I'm going to present some work that I've been doing in conjunction with Robin Bloomcoat over at Sandia. If you have any feedback about the talk, please tweet me at Travis_SCH. That would be super appreciated. So I want to start with a relatively benign observation. We've been hearing a lot about how we want to scale up quantum devices and quantum information processors. Kind of the elephant in the room is that as we do so, a full characterization of those devices is going to get harder. So this is a talk about state tomography, so let's talk about density matrices. If you have a device that produces a 1-qubit state, you have to describe that state using 3 real numbers. With 2 qubits, 15. With 3, 63. If you believe John Martinez, we're going to start building 100-qubit devices sometime in the near future. 4 to the 100 minus 1 is a really big number. So how are we going to get around the fact that in order to accurately characterize these devices, we just have too many parameters that we would have to fit? Well, thankfully, there's a statistical technique called model selection that we could use to make tomography more tractable. You see, a model, at least in the tomographic sense, is simply a set of density matrices. The purpose of model selection is to find that best model. So the focus of my talk is going to be on 2 very straightforward questions. What are the sets of density matrices that we're going to consider, and how are we going to define what the best model means? Now, lest you think that this is just me and Robin going off and doing statistics in complete absence of anything, realize that tomographers have been doing model selection all along. There is a trivial way to do tomography, and it is this. You pick your set of density matrices by simply defining the Hilbert space upon which they act. Of course my system is a qubit. What else could my system be? I don't know, but we can at least fit those numbers. Now, obviously, there are more sophisticated methods. A non-trivial way might be that you restrict your estimate to a particular subspace. So you fix the basis and you say, okay, all of these rows and columns, we're just not going to fit them. Just going to let them be 0. Those of you that are familiar with compressed sensing can see that that's probably a variant of restricting the rank of your estimate. That is, in its diagonal basis, you say, okay, it's only going to have a few non-zero eigenvalues. So what Robin and I have been working on is this case, where we're restricting our estimate to a subspace within the context of continuous variable tomography. So we've defined the sets of density matrices that we're going to consider. Now, finding the best model seemed like a relatively straightforward thing. And indeed, a year ago in San Antonio, I gave a talk in which I said, well, look, people, this problem is trivial. You just use these things called log likelihood ratios. You invoke this thing called the Wilkes Theorem, and then you're done. At the end of that talk, Nathan asked an extremely good question. He said, Travis, do you know about these things called information criteria? Why aren't you using them? Travis back then was very dumbfounded. Now we have an answer. You shouldn't, because it's the wrong thing to do. And we're going to tell you why. Well, we didn't investigate information criteria directly. We investigated a tool that a lot of people use for model selection. These log likelihood ratios and a result called the Wilkes Theorem. And what we discovered is that that key tool, within the context of state tomography, fails dramatically. We're going to get to all the definitions later, but suffice it to say that the amount of evidence that you would expect to see if your model contains the truth, as predicted by the Wilkes Theorem, would grow quadratically in your Hilbert space dimension or model dimension. We did a whole bunch of Monte Carlo, and we observed that this expected evidence sort of plateaus, which is really awkward. And we didn't really appreciate this a year ago, and it has kind of motivated the research question for the past year or so. How did this happen? How did we get this way? What is going on? And as we thought about it, we realized that essentially the problem is this. The foundations of model selection are well studied for classical inference. We start with some very standard assumptions. We say, I'm working in a parameter manifold that has no boundaries. I'm in the infinite data limit, so I'm quote-unquote asymptotic, or I actually saw this in a paper, asymptopia. Apparently it's the place to be. Within the context of model selection, we need to compare models. People use these log likelihood ratios to do so. These 2 bricks form the foundation upon which all of these sophisticated model selection techniques are built. In particular, the Wilkes Theorem, which predicts the expected value of this log likelihood ratio statistic in certain contexts. And then once you had that Wilkes Theorem, you know what you could do? You could get to the Holy Grail. You would get to information criteria that would provide you with a decision rule. It would tell you, this is the model that you should choose, and what's more, depending upon the information criteria you used, could tell you something about how wrong your model was going to be in predicting future data. Now, what happens? Well, unfortunately, things start to break down for the tomography of quantum systems. Some of these standard assumptions that we just blithely invoked and said, all right, let's go do it, they just don't apply. Why? Because quantum state spaces have boundaries. And these boundaries, they are unavoidable. It means that standard assumption of no boundaries in my parameter manifold, it's always going to be broken. So what we're going to do in this talk is we're going to talk about how can we prop up this Wilkes theorem, how can we provide a replacement for it that respects the fact that there are boundaries and gives us some sensible results. Yes, Nathan?
Well, I mean, there's many ways you can parameterize the state. You could say represent it as a sum of Pauli operators, and then
Sure.
all your likelihood functions just self-normalize.
Sure.
In that case, you wouldn't have any boundaries.
Sure, that's a very valid point. So maybe I'll say we're picking a parameterization in which there are boundaries.
Cool.
But of course, there's always this like positivity constraint. And so when we're talking about the states themselves, there are these unavoidable boundaries that you would run into. Future work that we'd like to do is actually make this information criterion so that way Nathan and I and everyone else that worry about these things would be happy. So what have we been doing? We've been studying how you could select Hilbert space dimension for continuous variable, aka optical tomography, to understand the behavior of log likelihood ratios and understand why this Wilkes theorem thing doesn't work. You see, continuous variable systems are a very nice sandbox for model selection in the following sense. Pick a representation. If you're an experimentalist, you might choose to use the Wigner function representation. I personally prefer just writing down density matrices. I find them easier to think about. In both cases, these systems live on an infinite dimensional Hilbert space. There are an infinite number of parameters that you would have to try and fit in order to fully specify these states. But the amount of data that you take is finite. And any statistician worth his salt will tell you that fitting infinite parameters using finite data is a very, 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 very bad idea. This lends itself to asking the question, how is it that we can find a small yet good model, only have some small number of parameters, yet accurately model the data we see? So the particular models we chose, as I said earlier, are called nested subspace models. We pick sets of density matrices that are spanned by the Fock states. So mathematically, the model M sub D is simply all the sets of density matrices that have support on the first D Fock states. You could say that these models come about because we're assuming that the states we're studying have relatively low energy. Now, I like to think in pictures for a lot of things. So if we drew a picture of optical phase space, these models are simply expanding concentric disks. This is the model that says we only have a 1 right here, aka the vacuum state. The red disk is the model that the state is contained within the span of 0, 1, blue within the span of 0, 1, 2, so on and so forth. If you think about it in terms of density matrices, all we're doing is just adding rows and columns when we write the state in the Fock basis. We studied heterodyne tomography as a particular POVM because, one, it's a common POVM that people use in tomography of continuous variable systems, and also because it has a very natural notion of enlarging and shrinking the support of the Hilbert space that it's acting on. So we did a whole bunch of Monte Carlo that involved picking some arbitrary but representative set of true states, simulating the POVM using rejection sampling, and then for every model, we would find the maximum likelihood estimate within it. Yes, Josh?
Travis, the heterodyne POVM is continuous. Did you truncate that as well?
How do you mean?
Well, the heterodyne POVM is like, well, it's not a projection, but it's a generalized measurement, which is like the outer product of coherent states.
Right.
So that's a continuous variable.
We can talk about that offline. By finding these maximum likelihood estimates within the models, now we're going to be able to compare them. And in order to compare them, we use these log likelihood ratio statistics. We're going to talk about comparing models to the true state. Now, there is a formula on this slide. I don't want you to be intimidated by it. All I want you to observe is that there's a maximization of the likelihood function in the definition of the statistic, hence the need to do some MLE. Now, you might ask, Travis, usually you don't know the truth in an experiment, so why are you talking about this? Well, thankfully, if you can compare models to the truth, you can compare models to one another. So maybe we have a small model, like the qubit model, that we want to compare to the qtrit model. We want to compute the statistic comparing those two, and we can do that by writing it as the difference of the statistic comparing each to the truth. Hence, we'll just focus on comparing models to truth. Now, we have this log likelihood ratio statistic. What about this thing that's called the Wilkes Theorem? The purpose of the Wilkes Theorem is to tell us that if our model contains the true state within it, then you can calculate the distribution of this statistic. It's going to be a chi-squared sub d squared minus 1 random variable. We're not going to worry about the definition of what the chi-squared distribution looks like. Suffice it to say that the important thing is that it has an expected value and you can calculate it. So what we wanted to ask is, okay, consider some very large n limit. What is the expected value of that statistic? We want to know these numbers, so that way we can compute this expected value in the case where the truth contains the model, which will then tell us how much evidence we would have to see in order to justify using that model to explain the truth. Yes, Scott?
I think I missed something because we know what the expected value of chi-squared distribution
That's right,
is.
we do. It's some like d squared minus, right? You say, Travis, like this is kind of, are you just simply confirming Wilkes? No, what we're going to show is Wilkes doesn't work. We're going to show that the numbers that Wilkes predicts for these averages are not at all what they actually are. And in fact, thank you for raising the obvious question. No, it's totally fine. I very much appreciate it. Because we want to see some evidence, right? So let's get to the actually kind of relatively interesting and new and really cool part of the talk. We talked about the statistics. We talked about the background. Let's talk about what Robin and I have been doing. Essentially, the Wilkes Theorem just incorrectly predicts the behavior of this statistic in CV tomography. So let's look at the non-XKCDF5 version of the plot that I showed earlier. Pick your true state as the super benign vacuum state. Simulate this POVM. Do MLE in Hilbert space dimensions 2 through 10. Pick many order 100 independent data sets. Compute this statistic. Average over 100 data sets. Get these very nice blue dots. Then ask yourself, what does the Wilkes Theorem say that these averages should be? You get something that looks like this. It grows quadratically. What the hell? This does not make any sense. You might say, okay, well maybe it's just this vacuum state, right? It's a special state. It's actually a state that's contained within the POVM. Well, we simulated many true states in many model dimensions. Plotting the empirical average on the x-axis and plotting the Wilkes prediction on the y-axis, we see that pretty consistently the Wilkes Theorem just sucks. It always predicts a number that is way too high, which means that when we try and formulate these information criteria, we're going to be horribly off in choosing the right model. So that's the evidence. And the takeaway from this is that the Wilkes Theorem just gives this wrong behavior. We can't use it for choosing Hilbert space dimension. And because information criteria are built on top of the Wilkes Theorem, you shouldn't be using information criteria either. So, I see Robin in the background. So, it's not sufficient to identify that there's a problem. You have to actually fix it. So let me show you how. We do so by observing, oops, computer, are you going to respond to me? Yes, great, thank you. We start by observing that Wilkes relies on just computing a Taylor series. So let's ask the most benign question ever. If I compute a Taylor series, do things behave as we expect? So we're going to take our Taylor series of the statistic out to second order, and we're just going to ask, okay, if I take my data and compute the right-hand side of this equation, and take my data and compute the left-hand side of the equation, do these numbers agree? Okay, left-hand side of the equation, right-hand side of the equation, they mostly fall along a good line. Okay, Taylor series out to second order, fully acceptable. Why do we do a Taylor series? Because we assume that our estimates are relatively close to the truth. Okay, next thing. Let's just ignore that first order term. We're just going to set it to 0. Well, things aren't looking so good. It seems that the empirical values are consistently just a little bit higher than what just using the second order term would suggest. It means that actually including the first order term is an important thing to do. We're going to ignore it for the purposes of this talk and focus on how we can understand why the second order term really tells us why the Wilkes Theorem breaks down. So now we have to do a little bit of math. The first part of math that I want to do is recast that equation in a much more comprehensible form. So we're going to start by saying, well, we have some second partial derivatives of things, so let's just wrap that up as a Hessian. Nice definition there. We're also going to realize that this equation is actually notationally wrong, if you think about it, because density matrices, when you do this Taylor series, need to be vectors in Hilbert-Schmidt space, so we'll put some Langle things on stuff, and then we're going to write this matrix element, essentially, as a trace, by defining what we're calling the fluctuation tensor. It's the tensor formed by taking the outer product of the difference between the true state and your maximum likelihood estimate. When you recast the equation in this form, what you see is that the behavior of the statistic depends upon the observed information H and the fluctuations F. Okay. Now, once we have this result, we can actually rederive the Wilkes prediction and then, as sort of an added bonus, as it were, discover how to make a model that fixes why Wilkes breaks. To do that, we observe that in the absence of boundaries, you get all the nice things in the world. So how do we do it? We start by just putting some expected values on things. We then argue that the expected value of a product can be broken up as the product of expectations. Or you can argue that the observed information is an unbiased estimator of the Fisher information, and so we're just going to pull it out. You then say, oh, well, there are no boundaries, so the fluctuations F align with the contours of the observed information. This means that essentially we are saturating the Kramer-Rao bound, which means that this fluctuation tensor has to be the inverse of the Fisher information, and voila! Using the Taylor series, we say the expected value of lambda is d squared minus 1. We recover the Wilkes result in the absence of any kind of boundaries. It requires that things line up and that we can saturate the classical Kramer-Rao bound. So where does this go wrong in state tomography? Essentially what happens is that boundaries distort state space fluctuations. We start back at the beginning. We essentially put the expected values on things, split up the expected value like that, and then you stop. And you say, well, we can't really do much. Because we have this boundary in state space that we're supposed to respect when we're doing our maximum likelihood, this fluctuation tensor doesn't have to align with the contours of the observed information. Or phrased another way, the observed information doesn't know about the fact that there are boundaries because we measured a POVM that's not really sensitive to it. So because things don't align, and we don't saturate the classical Kramer-Rao bound, we're kind of screwed. So we need to find some way to take this formula and do something useful with it that allows us to respect state space boundaries. And doing so is as simple and complicated as going to a basis, rescaling the state space such that the Fisher information is isotropic. Essentially, we're just going to rewrite this trace. Instead of HF, we'll go root HF, root H. It's equivalent to doing a basis change in which the Fisher information is isotropic. If you're uncomfortable with that, we're just using the cyclic property of the trace to rewrite it in a nice way. All sort of facetiousness aside, what's nice about this representation is that the tensor is now symmetric. And so we can diagonalize it, and it has all these really nice properties. So I wanted to motivate the next few slides in which we're really going to show you deep down why the Wilkes theorem doesn't work with a very simple example. So suppose that we were doing qubit tomography and we didn't know about the fact that there was this positivity constraint. What would the Wilkes theorem predict as these diagonal matrix elements? Well, for all qubits, you can't fluctuate their trace. So the identity component contributes 0. But for the sigma x, sigma y, sigma z contributions, you can fluctuate, so they would contribute 1. So that's what, that in this sense, this tensor is the identity, except we're projecting out the fact that you can't vary the trace. Let's do a basis change to go to the basis of matrix units, i.e. outer products of Fock states. It's kind of a more natural basis that we like to think about. So in that basis, you just turn your head sideways. It mixes the contributions of the identity and sigma z. That's all. You'd say, oh, well, where do we go from here? Well, you observe that the trace doesn't really care about the fact that there are off-diagonal matrix elements. We just sum these guys up. This is the basis of matrix units, so let's take these diagonal numbers and reshape them into a 2x2 grid. Yay! These are the numbers that the Wilkes theorem predicts for qubit tomography in the absence of boundaries, expressed in the basis of matrix units. What we're going to do next is walk through a few heat maps and actually look at what these numbers are for the data that we have. And what we discovered was that different matrix elements have different contributions. So pick the true state as the vacuum state, do qubit tomography. Remember, if Wilkes theorem were to hold, we would see 0.5, 1, 1, 0.5. We do not see that. But those numbers kind of look like 1, right? Right? Okay. What if we went to d equals 3? Again, same idea. Extract out those diagonal matrix elements, reshape them into a d by d grid. Well, those numbers kind of look like 1. Okay, one more. D equals 4. Those numbers look like 1, those numbers, not so sure about these guys. Now, admittedly, in 15 seconds, you probably couldn't discern the pattern, but if you stare at these for about a month, you will realize that there is a pattern, and let me show you that pattern by putting all of these plots on the same slide and taking out the numbers. We see an L. We see that somehow there's this notion of matrix elements that contribute a lot and matrix elements that contribute a little. This effect is actually very strong if you look for the d equals 10 reconstruction, which I'm plotting down here in the lower right. You see this big L, numbers that are kind of close to 1 or at least not 0. Lots of numbers that are 0, not what the Wilkes theorem predicts. You might say, okay, Travis, once again, you just picked the vacuum state, it's a special state. Let's look at other true states. Instead of getting an L, you might get a cross, you might get a larger L. It all depends upon essentially the rank of the true state and its support. And so we looked at this data and we said, well, is there a way to model this behavior that we could actually predict the expected value of the log likelihood ratio statistic in a way that respects state space boundaries? We did. We built a very simple model. It is the simplest model that you could think of. It says, look, the biggest numbers seem to be coming from these off-diagonal matrix elements that are coherent with the subspace upon which the true state is supported. So they contribute a lot. We kind of impose boundaries by realizing that it looks like these diagonal matrix elements also contribute some too. So in our model, what we're going to do is say, if you're off diagonal and you're coherent with the support of the true state, you contribute 1 unit of expected value. If you're a diagonal matrix element, we're going to do some Monte Carlo. You can ask me about that offline. The upshot of this is that we can write down a formula that computes the expected value, and it has these 2 terms. This formula is not good in the sense that it depends upon the rank of the true state. The Wilkes theorem was powerful precisely because you didn't have to know anything about the truth. And it reduces to the Wilkes theorem in certain cases. Our model does a lot better than the Wilkes theorem at predicting the expected value. So again, empirical average on the x-axis, predicted average on the y-axis. Wilkes theorem shown here in orangish color, it looks like. Way too high. Our model in blue, much better. Still some caveats. We can talk about those offline. Where does this leave us? Where have we come from? Where are we going? I think there are 3 key takeaways. The first is that if you're doing model selection in quantum state tomography, you probably shouldn't be using the Wilkes theorem. You probably shouldn't be using information criteria. It's just not the right thing to do. We have managed to build a simple replacement that does much better. This replacement is derived by kind of counting up matrix elements that are coherent with the true state and recognizing that different parameters in the density matrix have different contributions. What I didn't get to tell you is we strongly believe that those contributions are actually sample size dependent. So what have we been doing? We've been building a foundation upon which we can do model selection correctly. We've been restacking that pyramid. We're trying to provide a replacement for the Wilkes theorem. We might even try and prove a quantum Wilkes theorem as you work. Maybe, maybe not. We can probably build some kind of quantum information criterion on top of these results. And a small aside, it would be very interesting to study large dimensional asymptotics, the field of statistics where both the number of parameters and the amount of data that you have to fit those parameters is going to infinity. And because we're building this foundation, we are advancing the state of the art in quantum tomography. As we build bigger and bigger devices, it's going to be harder to characterize them. But our saving grace is that they only have so much structure. So let's try and model that well. Thank you for your kind attention.